Alright, in this video we give just a brief look at vector fields and how these will intuitively lead to new kinds of integrals in the chapter 16 section. Alright, so what we're seeing here are some vector fields that are a bit more complicated. Vector fields don't just have to be two-dimensional, they can also be three-dimensional, so we could have a three-dimensional vector field. So each entry of this vector could be a function of x, y, and z, right? And the example we're seeing here is that f1 is equal to 0, f2 is equal to 0, and the third entry of the vector field is the constant 1. And this will indicate that at no matter what point P that you pick, there will be a vector at that point P that is 0, 0, 1, that always points up. So here's a vector field that always points up, and here we can see a vector field that, depending on the y value, right, here's y is equal to 0, depending on if you are on the right side of that y equals 0, the vectors will point to the right, or if you're on the other side, the vectors will point to the left. And because z is equal to 0, we are getting that copy. We're getting this copy of the vector field in every copy of the plane z equal to whatever constant you pick. So for z equals to a constant, the vectors are always pointing in the y direction, just positively or negatively, right? And that is repeated for every value of z. So three-dimensional vector fields sometimes are a little bit more challenging to see, but the general idea is just to have in your mind, the idea that, that vector fields can exist in three-dimensional space. Oftentimes they look we can see here that you look at them and there's vectors pointing in all different directions, and there's really not much sense to make of them. They're kind of hard to see. The one you may have a slight chance of kind of getting a good sense of is, if we look at this three-dimensional vector field, notice that the x and y entries were negative y comma x. So that indicated that in the xy plane we were having that circulation vector field, that one that looked like we had kind of circular motion, right? And the fact that we've added a z entry now to this vector field indicates that this vector here, while it's circulating, also has some lift up in the z direction, right? So what we're kind of finding is that this vector field circulates and kind of will lift you up. So it's kind of like a helical vector field. So we're still rotating, but we're also being lifted up in the z direction. And then there are just vector fields that you just can't make any sort of sense of. You just say, well, that's interesting. Kind of looks like the vectors are kind of moving all around in different directions in the XYZ space. Okay? So with just these general pictures of vector fields in mind, we can start to mix in and build up to the different kinds of integrals that we might see. Okay, so the top two vector fields, notice that there is a vector field, a two-dimensional and a three-dimensional vector field shown. And then there is also this curve shown. Okay, so what we have here is a mixing of a curve that's given to you and a vector field that's given to you. Okay, and the kinds of integrals that you can do if you have a curve and a vector field are called line integrals of vector fields. Okay, so we've done line integrals of scalar fields, right? So you'll recall that we've done the integral along a curve of a scalar function ds, right? So this was a scalar function. That's what we've done in the past, and that was interpreted as the mass of the curve C. Well, once you have a curve and a vector field, we can do a new kind of integral called a line integral of a vector field, and we'll have to put dot product with this thing called dr, and we'll have to address that. But there are line integrals of vector fields, and the interpretation of these will be given as the work. They're kind of our work style integrals. Work in the sense of physics. Work is equal to force done over a distance. Okay. Then we can see here that there is a mixing together of vector fields, that the vector field will be given. You can see that as the blue arrow in three-dimensional space. And then we also have a surface. A surface is given, or maybe even a part of a surface. So here you can see that we've got this donut shape, but we've got this particular patch on the donut given, and so we would have a vector field and a surface. And once you have these kind of ideas, we can do something called a flux style integral, and that's going to look like a double integral of a vector field f dotted with the area element over a given region of that surface. So we're going to in the coming sections return to line integrals but of vector fields, and we will kind of begin introducing the idea of a flux style integral. And a flux style integral is essentially just a thinking of the vector field as perhaps like a wind vector field, or a force vector field like an electromagnetic field, and you have this vector field at all these different points, and you have maybe a part of the surface, and the question is how much of the vector field passes through the surface. And that is the essence of flux. Flux is how much of the vector field crosses through the surface. So that is the general essence of a flux integral, and it will be this mixing of a surface and a vector field given, and then there are line integrals which will help us compute work. So these are the different kinds of integrals we'll see in the next upcoming videos, and well, we'll just hold on and see what happens.